Welcome to qnawire.
All right, we've got a benzene ring, the three carbon chain coming off of it, and we've got our sulfonamide. What is this? Like a tosylate? I guess this is a triflate. Yeah, and we've got a triflate, and we're reacting it with ethanol. And the question is this going to proceed via SN1, SN2, E1, or E2? So when I think about SN2 and E2, the first thing I'm looking for is my base or nucleophile strong? And usually that comes down to, is it charged or is it neutral? If it's neutral, we're looking at a little less likely to be proceeding via SN2 or E2. Here we have ethanol, which is neutral. It's not a charge. That would be the charged form might be like sodium ethoxide, for example, right? That's going to be a much stronger nucleophile, more likely to proceed via SN2. But we don't have that. We have ethanol. So it doesn't immediately jump off the page to me as being SN2 or E2. The next thing we can look at, or actually usually the first thing to look at, is the substrate. Is it tertiary, secondary, primary? If it's tertiary, you can rule out SN2. If it's primary, it must be SN2 or E2. It can't be SN1. If it's secondary, it's a little more nebulous. We don't know for sure. But there's something else going on here. It's not just secondary, it's also allylic. Now, recall that carbocations, well, first recall what an allylic position is. That just means that it's one carbon away. So this is the allylic position. It's one carbon away from a conjugated system or even just a double bond. And the idea is that if in fact this triflate left on its own via, SN1 or E1, that it would leave behind a carbocation, and that normally you'd be like, we're looking at this molecule now, so we're pretending that it's a, primary carbon. You might think that it wouldn't be possible for something to leave on a primary carbon, but in fact, in this case, since the charge can be stabilized through resonance, it's actually more stable. This positive charge here is more stable than even a tertiary positive charge, right? So the long story short is that this particular carbon that the triflate is attached to is particularly stable in its carbocation form, which leads me to believe that this is probably going to proceed via SN1 or E1. And then the next thing to really consider is this a better base or a nucleophile? Are we likely to get um, either the E1 product or the SN1 product? Okay. So the final thing we're going to consider, basically deciding between E1 and SN1 at this point. And the final thing that we want to consider, SN1, is this solvent that we have. Like, recall that we're in ethanol, and ethanol hydrogen bonds, and it's a polar protic solvent. Well, polar protic solvent typically decreases the nucleophilicity of the nucleophile in this solvent. Well, in this case, ethanol is both the solvent and the nucleophile, but in either case, the nucleophilicity of this solvent will be decreased, which means it may err more towards the base side. I think the final, probably most important thing in deciding versus E1 versus SN1 is look at the products. Okay, like consider, what if it does go through SN1, right? Okay, that's the SN1 product, the substitution product. The elimination product is a conjugated system. This double bond is particularly stable because it's conjugated to the entire benzene ring. That's going to be a driving force thermodynamically to favor E1. The elimination product is just so much more stable than the SN1 product because we're increasing the size of this pi system, basically. Right? We went from 3 conjugated double bonds to 4 conjugated double bonds. So this is, at this point, heavily favoring E1. This is going to be an elimination reaction in which the triflate is going to leave, and then we're going to see deprotonation at this carbon to create a double bond afterwards. And I drew it all in one step, but it's not E2, it's E1. I'm just showing it all in one molecule. But yeah, there we go.